This video is about revising the small signal circuit. Suppose you have a curve y as a function of x, and if I am asked to do some approximations about it and linearize it, I would just make a tangent at this point and use that y is equal to mx plus c around this operating point. This m is nothing but dy by dx. It is nothing but you are approximating this curve as this line in this region. So approximating this whole curve in this region with a tangent. To know the limits till which you can use this approximation of tangent, to justify it, you just calculate the limits of x. That justification we can give from Taylor series. Suppose if I have to approximate f of x around x is equal to c, it's nothing but f of c plus f dash of x at x is equal to c into x minus c plus f double dash of x at x is equal to c into x minus c whole square divided by 2 factorial, and the terms will go on. The tangential approximation is nothing but this, and we are ignoring all other terms in the Taylor expansion. What this means is this term itself is the dominant one in the whole expansion. What that means is f dash of x at x is equal to c into x minus c itself is greater than sum of all other terms. You can start with f double dash of x at the rate x is equal to c into x minus c whole square divided by 2 factorial. So once you solve this expression, you will get an inequality for x. Suppose if you get x less than 2c, so this would be the 2c limit on both the sides. So this side it's 2c and this side it's 2c. Now let's try to solve one circuit with graphical approach of calculating operating points. So in this circuit, whose IV characteristics are like this, it has different resistances at different points. In fact, this is a negative resistance because as voltage is increasing, there is a decrease in current. So to solve it, this voltage is VO, this is phi, this current I is phi minus VO divided by 1 kilo ohm, so into 1 milliamp. If I'm plotting this phi minus VO, it's this. So my operating point is this. I just have to linearize it about this point. The curve is already linear. This resistance is nothing but delta V divided by delta I. So this resistance is nothing but change in voltage by change in current. Change in voltage is 4 minus 1 divided by change in current is, when it's 4 it's 2 minus 3 milliamps, so it's 3 kilo ohms with a negative sign. So in my small signal model, I will just use a resistance of minus 3 kilo ohms in place of this device. 1 kilo ohm stays as it is, and this is 0.1 cos omega t. Let's call it Vin. So if I have to write VO in terms of Vin, it's just a resistive network. VO is equal to Vin into minus 3k plus 0 divided by minus 3k plus 1k. Simple resistive divider equation. So if you are given any circuit with any different kind of device with its current versus voltage characteristics, just have to find its operating point and then linearize about that point. Differentiate it. If you dou I by dou V is 1 by R. Differentiate it if it's not linear. Since it is linear here, I am just using the slope which is same as the differentiation, and replace with this resistor in your small signal model and calculate it. That's it.